Okay, so before concluding this chapter, okay, so actually this is the last chapter in the electrostatics. Okay, so with so many variables. Okay, so many fundamental variables. Okay, even though chapter 25, 26 are still electrostatics, but just to apply all we have learned for two of the three most important circuit components called the capacitor and resistor. So here, we try to summarize the four most important variable that we have already covered. Okay, we have an E field, we have a potential, we have potential energy, we also have Coulomb's law, Coulomb's force. Okay, so which all these formulas have similar expression but not quite the same. Okay, so here there are some symmetry between them. Okay, so of course we assume the two particles cases. Okay, so the upper row, okay, these two are vectors. Okay, the force, the Coulomb's force is a vector. The E field is also a vector. Yeah, but for the lower row, potential energy is a scalar. Okay, electric potential is also a scalar. Okay, so horizontally speaking, okay, they have a relationship F. Okay, this is F. Okay, so F is here, E is here. Okay, so they are proportional to each other. F is Q0 times E, Q0 times E. Okay, similarly for the scalar, so for the scalar pair, okay, potential energy here, electric potential is also here. Okay, so they have a also they are proportional to each other. U equals Q0V. Okay, so in that case you can see on the right side we only have Q in the numerator, but on the left side we have Q0 or Q1, Q2, depending what you want to call it. So we have a multiple of charges on the left side and then a single charge on the right side. Okay, of course K are all the same. Okay, and then finally, vertically speaking, okay, in this chapter, okay, or even in the chapter 22, actually in chapter 22 we know voltage or electric potential is a negative E dot ds. Okay, negative E dot ds, this line integral. And then in this chapter we also know that this you can also make it like this is integration, this is derivative, but in high dimension. Okay, so the inverse operation of the line integral is actually the gradient operator. Okay, so to take the gradient operator to the electric potential, take the minus sign, will become the E field, or take the line integral of the E field along the ds along a path, and then take the negative sign is the voltage. Okay, is the potential. Okay, so they are inverse to each other. Okay, so in that case we have like, okay, so from here to there can be like a derivative. Okay, a derivative, or I should say from here to there. Okay, take the derivative of the V. Okay, but in high dimension become the E field. Okay, so R to the negative first power become negative second power. Okay, similarly, for the force and potential energy, it also have a similar expression. So F equals ds. Okay, I mean F dot ds is the work done. Okay, so take the minus sign will be the potential energy. Okay, so or inversely we can write it as the force is actually the negative gradient of the potential energy. Okay, so these and these are just changing the variable from E to F, and then to change the V to U. Okay, so they are slight. So they are actually have the same form. So for the upper row, we have R square in the denominator, but for the lower row we have r in the numerator in the denominator. Okay, so these four formulas are similar, yeah, but they are like 2 times 2 combination of the QQ 0 and also the r squared. Yeah, so finally we have 2 additional examples to conclude this chapter. So for this one, a plastic rod has been bent into a circle of radius r equals 8.2 centimeter. So it has charge Q1, okay, Q1 is a positive value, uniform distribute along 1/4, okay, which means this part, the green part of its circumference, and charge of Q2 distribute along the rest of the circumference. Okay, so Q2 along among the rest of the 3/4. So with V equals infinity, V equals 0 at infinity, what is the electric potential at the center C of the circle? Okay, so this point we just need to know, okay, the radius is r. Okay, so the good thing is potential is a scalar, so it is easy to compute. Okay, even though you try to cut it out, okay, but actually you can find every part of small charge packet, okay, generate the same potential, and then they add together, so it's just like a multiplication. So finally it turns out to be like the V at the point C, okay, V at the point C is K times Q1 over R, and then plus negative 6 Q1, Q2 is negative 6 Q1, also over R. Okay, so this is the great thing for the potential, is a scalar field. So calculating the potential at point C, okay, yeah, actually it is with equal distance to the whole circle, so it turns out to be just a simple formula. Okay, so it turns out to be negative 5Q1 K, okay, and then over R. So we can plug in all the number, so which is 8.99 times 10 to the 9th power, and then we have negative 5 times Q1. What is Q1? Q1 is this one, 1.2 times pico. Okay, pico again, 10 to 10 negative 12 power. And then R is 8.2 centimeter, change it to meter, 0.082. So this is negative 2.3 volts. Okay, so this is easy. You just need to know, okay, for the potential, just related to the distance, okay, and that is scalar. So okay, suppose the point is with an equal distance to all the charge distribution, then okay, it's just adding many constants together, just like a multiplication. Okay, for the part B, okay, what we concern is we have a D here, so what we want to find is the potential at point P. So this is still very easy. Okay, what we really need to know is this R, and then according to Pythagorean theorem, R is a square root of capital R squared plus D squared. Okay, R equals square root of R squared plus D squared, okay, which is 8.2 square plus 6.71 square. Okay, so here you may ask why you use the centimeter here. Okay, why you use the centimeter here? Because usually for most of the case we need to use the SI unit, which is meter rather than centimeter. But here, for this Pythagorean theorem, okay, this is the length, this is length, this is also length. Okay, so we don't actually change the dimension. Okay, change the dimension. So actually, if we try to keep it, this is centimeter, this is centimeter, so this is also centimeter. Okay, of course, if you are very cautious, okay, so you can change it to 0.082 square plus 0.0671 square. Okay, finally come up with a meter. But here we can actually make it like 10.6. Be careful, centimeter for the R. So finally, VP will be negative 5Q1. Okay, I don't try to repeat because it is just like Q1 minus 6Q1. Okay, to be negative 5Q1. and then times k, and then over small r. So which is 8.99 times 10 to the 9th power, and then times -5 times 1.2 times 10 to -12 over 0.106. Okay, so even though we use centimeter, but here we change the dimension, so we really need to change it to the SI unit, which is a meter. So 0.106 here. So finally, -1.78 volts. Okay, so this is almost the same. Yeah, but just change the point. Okay, but yeah, still the distance from point P to the whole ring is still equal distance as long as the point move along this z-axis. Okay, the axis of this circle. Yeah, so this is the first one, and then the second one. Okay, so a plastic disc of radius r, okay, is charged on one side with a uniform surface charge density sigma. Okay, we have sigma to be the charge density, surface charge density, and then 3 quadrants of the disc. Okay, 3 quadrants, 3个象限. Okay, of the disc are removed. With v equals infinity at infinity, v equals 0 at infinity. What is the potential due to the remaining quadrant of the at point P, which is on the central axis of the original disc at distance d, okay, from the original center? Yeah. So here, we know that v will be this one for the full disk, but here we only have one quadrant. Okay, one quadrant. So which means that v should be a quarter to the whole. Yeah, as much as we know v is a scalar, which means that due to symmetry, this quadrant should be the same as this quadrant should be the same as this one, should be the same as, yeah, I mean the potential generated by this quadrant, generated by this quadrant, generated by this quadrant, generated by this quadrant. All these 4 quadrants generate the same potential at point P. Okay, they will not generate the same E field, yeah, because for this part they will generate E field like this part generate but E field to there, this one generate, I don't know how to draw, and this one generate the E field. Okay, all are pointing to different direction. Okay, so that part of the XY component cancel each other. Okay, so for the E field, it is not easy to calculate the E field generated by this part, but for the potential, it's okay. As much as V is a scalar, and then all these are symmetrical to the point P. Okay, just like rotating. Okay, so the relative position are the same. Okay, so all these 4 quadrants generate the same part of V, which is 1/4 to the whole, to the potential generated by the whole disk. Okay, so which will be 1/4, and then times sigma is 7.73 times 10 to -15 over 2 times epsilon naught. We seldom use it individually. 8.85 times 10 to -12, and then we have a square root of z square. Okay, z square is actually d here. Okay, so which is 0.259 square. And then R, where is R? R is 64 centimeter, which is 0.64 square, minus Z is actually capital D, 0.259, okay, like this. So it is actually 4.71 times 10 to -5 volt, okay. So this one just to let you know, okay, these 2 additional examples just to let you know that, okay, computing to the potential is always easier than to calculate the E field, okay, but as long as we know the E field along an axis, then we will be able to take the derivative. But of course not for this case, because here we only know the potential at this point. We are not able to take the derivative here yet. Of course, you can try to change it a little bit so that you know the derivative okay, yeah, by using the definition of the derivative. Yeah, but only a point, okay, not the whole axis. So which means that calculating the E field at this point is not that easy. Okay, so here we finish.